Welcome back to Retro Depot. This is episode 2 of the tutorial on building an 8-bit Z80 computer. Today we're going to be going over some of the flaws that we made in the last episode whenever it comes to the circuit design. We're going to be changing up a few things and talking about some of the logic behind why we're doing things the way that we're doing them. A little bit different episode today. It's not going to be quite as long as the last episode. Mostly we're going to be going over, just a couple of small changes that we need to make, a couple of the changes in the parts that we're going to be using, and ultimately what our final goal is going to end up being with this particular computer as far as the way the AVR interfaces with the Z80. Now there may be some things that still change over time, and that's fine because as I mentioned in the last one, these things kind of develop over time. You kind of build an idea and then you build upon that idea, and you have to change a few small things throughout that course. But the basic idea we're laying out today. So I hope you enjoyed the video. Remember, this is episode 2. If you haven't watched episode 1, you need to go back and watch that episode first. That's going to lay kind of some foundation for this one. And then in the upcoming video, we hope to be actually prototyping this circuit in order to be able to see if it actually works the way that we intend for it to do so. And then we'll have to play with some software and see how well it runs. After that, we can work on putting together a board layout and then go through the process that we would need to do in order to send this board off for production. So enjoy the video, and of course, as always, any questions at all, ask them below. Let's get started. So, in the last episode, we put together this circuit here, and there's a couple things that I noticed afterwards that we actually need to change. So I'm going to go ahead and start off with a few details that I actually noticed. First off, we're going to need to change the memory circuit here. The decoding scheme, and the reason for that being is because I want to keep the chip count low on this, because I plan on prototyping this before I actually design the board and send it off for manufacture. So we need to actually slim this down a little bit. And what I was thinking is, because we don't actually need most of these, we can use a single 74HC138 in order to do the memory decoding, and we're going to go over that here in a bit, but that's going to save us one chip, and that's important because we're going to need to add a chip to this circuit over here. Now what we're going to need to add is going to be a octal latch, and the reason for this is pretty straightforward. Because we are going to be using this to take control of the bus, and we also would like to have some I/O, for an example, SD card, if you will, we need to free up pins 5, 6, 7, and 8, which means that we're not going to be able to use this as the lower port of the address bus. Instead, what we can do is we can actually use port A as the lower address pins, and then use one of these pins over here, probably pin 4, as a latch, so that we can latch the high address bits and then write the low address bits during any type of DMA cycle. And of course we also need to change some of the pins here in order to make this a little bit more conducive for our purposes. Now, there's a couple things that we need to actually change as well. I've decided to do away with the concept of trying to read and write I/O, read I/O from the AT Mega, and the reason for that being is because it's going to be a little bit hard, and I'll have to explain this to make you understand it, but the simple way of thinking about it is, when you do an I/O read, you're going to be asserting the I/O pins, and that's going to cause the ATmega to realize that there is an I/O function, and it's going to know it's going to be an I/O read. It's going to put that data on the data bus, and then it's going to have to release the I/O chip enable and the I guess you could say the wait state that it's going to create. But the problem with that is once it reads that, then that data is still going to be on the bus during the next Z80 cycle, which is going to conflict with the memory devices here. So it's kind of a bad way of doing it. But instead, what we can do is we can actually, for any type of I/O, whether it be a write to the Z80, for example, to send to the serial port, or to even say, hey, I want to know what is on the SD card. Whenever it does that write, that won't be a problem, because it's simply going to be reading the status of the data port pins. However, when we want to do a read, instead what we can do is we can first do a write to a specific register, and then at that point, once the ATmega decides which register it is, it can determine whether or not it's going to be a read cycle or a write cycle. So it would essentially be the same thing as the Z80 SIO. In order to read the status port of the SIO to determine whether or not there's data present, you would first write to a register and then read a bit. Now, what we can do with this is a little bit different. We can write to a register. The Z80 realizes what it needs to do. It then asserts the bus request line, and then it releases the flip-flop here's wait state, and that allows the control to go back to the Z80, which then notices that the bus request line has been pulled. It allows or acknowledges that with bus acknowledge, and then allows the ATmega 16 to take control of the bus through DMA, and then we can actually write that data to a specified location within the memory chips, and at that point release control of the bus back to the Z80, which then goes in its program to go read whatever that memory location is and figure out what the data is. So it's I think it solves a lot of problems, but it means that we are going to need another chip, and that means that we're going to be handling almost everything in software. We're simply going to write to a specific register and let the ATmega or the AVR determine what it is that we're wanting to do. So that means that we need to get rid of some of these chips here, and we need to add some others. So chip count's going to be about the same. It's going to be what have we got here? 4, 5, 6, 7. It's going to be 7 chips, but it's going to give us a lot more, I guess you could say, wiggle room as far as the I/O handling is concerned, because we're handling everything in software. And similar to an 8080, we don't have an I/O space, we only have a memory space. So we're basically using DMA in order to put these values into memory. Now, I'm not sure how well this is going to jive with operating systems like the I guess you could say operating systems like CPM. It may work well, it may not work very well at all, but we are going to have to make those changes in order to be able to make this thing work the way it should. Now, we're still going to be able to keep our 6 megahertz clock here, and this schematic here is going to be pretty much the same. The only difference is we are going to be using the not Q output as the wait line, and the reason for that being is because we have to basically interrupt any further T states by the processor. And this is a pretty simple way of doing it, I think, because it is technically a memory fetch. So we're essentially just telling it, hold on, we have to get this information out on the bus before, or we have to read this information from the bus before we're going to be ready to go. So it's an interesting way of handling it. I've looked at some of the other AVR projects out there, and they don't do it this way. Instead, it looks as though they are, I'm not sure what they're doing. There's the Z80 MBC project, which is fairly similar to this, but it uses a single 64 kilobyte RAM chip, and I think it uses AND gate in order to create what appears to be a exclusive NAND or exclusive AND, if you will, circuit. I'm not sure. But anyhow, we're going to toy around with this circuit a little bit. I'm going to, like I said, replace the memory decoding, and I'm going to add in a, I guess you could say, a data address latch here in order to be able to generate those signals. So we're going to go ahead and do that, and I'll be right back, and we'll see what we need to do next. Alright, now we've fixed the circuit, at least brought it up to what our new specifications are. Now, let's take a look at the address decoding. We've got a 74LS138N, which is a 3 to 8 decoder. Now, it has a couple chip selects here. Pin 6 is going to be high enable. So if it's low, this chip would actually be disabled, so we want to pull that high. Pin 4 and 5 are actually low enables. There's two of them, and we can tie those directly to memory request. That way, whenever it goes low during the memory cycle, it will go ahead and activate this chip. Now, we don't need to worry about inputs 2 and 3 because we're only going to be decoding a single line. And A15 is going to be our basically A input. So whenever this is low, all pins will be high with the exception of Y0, meaning that we're going to be accessing our low RAM. And if A15 is high, all pins will be high with the exception of Y1, which is going to be our RAM high enabled. So that's it for the memory decoding. We've taken two chips and we've shrunk it down into one. I typically don't use the 74LS138, or in this particular case it's going to be the HC, so let's go ahead and rename or give that a different value. Won't take but just a moment. There we go. I typically don't use that chip. I usually use a PLD or something that likes to do my decoding, but in this application it actually is a really good fit, so we're going to go ahead and use that. Now down here what I've done is I've revisited the address port because we needed the extra I/O here. Now obviously we're taking port A, which is our analog port, and we're using that as digital inputs and outputs, and we've made this address as line 0 through 7, so that's our low byte for the address. Now we've kept the data port, and down here in port D, obviously we have transmit and receive, memory request, I/O chip enable, which is the it's going to be the wait state enabler and the signal to the AVR that there's some type of I/O request that needs to happen. We have bus request and bus acknowledge, which those are going to be important because we're going to have to take control of the bus in order to be able to put data into memory. And then obviously we have the reset line here because we need to be able to reset the Z80 in software. We also have the address latch, which is going to be used to latch our high address bus, similar to the 8085 or the various x86 processors. We're essentially putting data on the low, or address on the low address lines, and then we're latching that data in to create the high byte for the address. And of course we are using a 74HC574 because this is a very good chip to do that.
and it's only going to be active when we actually are in the bus acknowledge cycle. So if it's not being acknowledged that we're doing a DMA transfer, then this chip will be essentially useless. It's going to have these right here as high Z, or high impedance, and it's going to make whatever is stored inside this latch irrelevant to the bus. So that's very important. Now, in addition to that, we also need to be able to clear the IO chip enable and the wait state so that the Z80 can take control of the bus again. So we have our clear line up here on pin 3, and of course we also need our read and write. That way we can read and write data to the memory bus here, and we can also determine if there is some type of IO function, what exactly it is that the Z80 is wanting to do. Now, we do have an open pin here, so we are, at this time at least, we have 1 bit of IO that we can use the AVR for, in addition to the SPI pins here, which can be used for not only the SD card, but also in-circuit programming of the AVR, so that we don't have to pull it out of its socket every time that we want to rewrite that data. The clock line has remained unchanged. We still have our 6 megahertz clock to the Z80, and of course we have our reset circuit up here, which we will probably go ahead and add a switch to this, but we don't need it at this time because we are just essentially designing our circuit. We don't really need to have a switch on here just yet, but we will eventually add one. We will not, however, need one for the Z80 because we are going to be handling that function by the AVR. It's going to be the chip that's responsible for resetting the actual computer itself. So this is essentially going to take over a lot of the things that we would otherwise need to do. Now, a couple things that we need to start thinking about is how we are going to handle things in software. And the reason why that's important is because it's going to help determine what you're going to need as far as a circuit goes. The first thing that we have to think about is when this boots, how is it going to happen? So obviously, as it boots up, the AVR is going to need to essentially reset the Z80 because we have to get it into a known state, and it's going to have to request access to the address and data bus. So it's going to actually reset the Z80 as it's set low for the reset cycle. It's also going to set bus request low, and then it's going to release the address or the reset pin to high. And at that point, the Z80 should recognize that there's a request for the bus, and it's going to go into its basically high Z state. Now at that point, we can begin latching the high address and then putting our address for the low pins on the A0 through A7 and begin loading memory, because we have access to the bus, and of course we'll have to assert memory request and also use our write pin for that. But once the data is loaded into memory, into these RAM chips that are being decoded by the 74HC138, once that's done, we can then release the bus request. But before we do, we're going to want to hold down the reset, and that's actually going to essentially reset the Z80 again so that it begins at the bottom of memory. And once both of those pins are low, we can then release bus request, and the Z80 should be up and running at that point. Now, the two other things that we need to look at are the IO reads and IO writes. Now, with the IO read, it's pretty straightforward. We do need to essentially do an IO function, which is going to set the IO chip enable and the wait state. And of course, we haven't put our wait state in here. We actually, or our wait line, we actually need to connect this right here to wait. And the reason for that being is because when you reset this, and we're probably going to, when we reset this, it's going to put IOCE to low. So it's only whenever this goes high that the AVR is going to acknowledge that there's an IO state. But this line here, the not Q, is going to be high. And when we clock this, it's going to swap that around, and this line is now going to be low, and this is going to be high. So that tells us that this right here can be used for the wait. So let's go ahead and do that at this time. Let's just go ahead and add a little branch out here, and we're going to put a tag on it, and we are going to rename it as wait. Okay, that's good. So now the next thing that we need to do after we actually acknowledge that there's going to be a wait state in IO is the AVR actually needs to read the port that's being requested, and of course it's going to do that on the A0 through A7 pins. And once it reads that port, it's going to determine that it needs to do a bus request. So it's going to go through the bus request cycle and modify memory as needed. Once it's done, it has to then clear this wait state here. Well, actually, it's going to need to actually set the bus request pin and then clear this. And the reason is because the Z80 is actually going to have to finish its cycle before we can actually take control of the bus. Now, having said that, this wouldn't actually be a IO read, it would be an IO write. So we're writing to a particular register. And of course, whatever data is on the data bus could also tell us what aspect of that IO port it wants. So for an example, let's say that you have the Z80 SIO. We'll use that again as a good example. So you would write to the command register a particular address, and then whatever that address is, it would then put that into the data register, and then you would read back out of that data register, and depending upon the bits that were set, it would tell you what the status of the SIO is. This is going to be very similar to that. We're going to write to the AVR at a particular port and a particular value, and it's going to then in turn release control of the bus, and then it's going to enter a DMA cycle. It's going to store that value back into memory at a particular memory address, and then it's going to give control of the bus back to the Z80, which can then be used to access that memory location and read that data and then determine what it needs to do from there. So once we've actually modified the memory and we've acknowledged the bus and gone through that whole DMA write portion, at that point it's the end of that cycle. But for an IO write, it's pretty straightforward, and it goes right back to what we were talking about before. The Z80 is going to write to a particular register. The AVR is going to initialize the wait state. Well, not really even the AVR. It's going to be the Z80 that's initializing the wait state, because it's going to be automatically clocked. At that point, the AVR will read the data. It will do whatever job it needs to do. It's going to clear the wait state and the chip enable. And at that point, if there's no DMA, it's just going to end. But if there is a DMA cycle, it's going to go ahead and access that memory and do whatever it needs to do, release the bus back to the Z80 and end. So we've kind of come up with a pretty good scheme here as far as exactly how the AVR is going to interact with the Z80. And of course, some of this stuff will change because we're going to be doing it in software, and we have to come out with a real good flowchart with exactly how it's going to function. But we at least have an understanding of how we intend for it to function so that we can continue with our software. But for the most part, I think the circuit is actually good. I don't really see any major changes that need to happen. At least not at this time. Like I said, we do have one pin that's still open on the AVR, and we are currently at 1, 2, 3, 4, 5, 6, 6 chips. I think that's right. 1, 2, 3, 4, 5, 6, 7. No, we're at 7 chips. Yeah, 7 chips. So yeah, it's coming along nicely. Of course, we're going to have to add a SD card circuit, which that'll be pretty straightforward. Obviously, we need the SD card connector, and then we'll also need a total of, I believe, 6 resistors. That way we can do voltage dividers going to bring it from 5 volt down to 3 volt. And then we will also need a voltage regulator to give that circuit 3.3 volts to the SD card. And I think that's pretty much it. We may add another chip in order to be able to connect directly to USB. That may be something that we do, or we may just go ahead and leave it as TTL serial. I'm not certain at this point. We'll figure that out a little bit later. But as far as the circuit itself goes, I think this is actually going to work. So the next thing that we need to do is obviously add in the SD card and the resistors for that, and some type of voltage regulation. So at this point in the project, I think that's what we're going to do. I'm going to do that off camera to save time. That last video was about an hour long, so I'm wanting to trim this one down just a bit. But once we do that, I think that we should have a circuit that will work for us. And of course, we'll have done it with a total of 12 resistors and 7 ICs. So that's pretty good. Now we're going to have to write all of the software, and of course the Z80 code we're actually going to probably store in memory, or something else that we could do is we could store that data in the SD card as a binary file, read the data from the AVR and plug that data into the Z80. So that may actually even save us from having to use the program space of the AVR to program the Z80. We might be able to again read that data in and store everything on the SD card, but we are going to have to write the program for the AVR in order to do that. So it is going to be a a while before this project is done, but we're coming along nicely. I don't really anticipate having any problems with this. Obviously we have a address latch here that we're going to have to manage, but I think that's going to be able to be done with the way it is currently. Outside of that though, I think everything looks good. I don't really foresee any problems with this. I think that we're going to be safe. And with the SRAMs, we've got a couple options here. We can either use the narrow SRAMs like I used on the G80S and G80 USB, or we could use the standard 62256 style SRAMs from back in the 80s, the wide ICs. They're both 28 pins, and the pinout is identical. It's just one is narrow, one is wide. Depends on how much space we want to save. I'm thinking about using one of the prototyping boards for the G80S and G80 USB to build this circuit, at least prototype it, simply for the fact that it already has a micro SD card slot on that. It should be simple for me to use. It already has the voltage regulation on there, so I think that's probably going to be the best bet. I anticipate this entire circuit being primarily through-hole. If we may end up using, for example, a 1117 voltage regulator for the 3.3 volt, but that's easy for anybody to do. And then if we do include USB, we may actually use a CH340G. The reason for that being is it's a easy chip to solder on the board, and it doesn't take up a lot of space. And that would give us USB access. Something else that we could do is also, try to interact with, for example, another micro in order to do video out. But this is just something to play with. We can access this over serial for the time being, but it should be interesting. And we're coming along. So let's go ahead and pause the video at this time, and we're going to go ahead and add in that circuit for the SD card and the voltage regulation, and then at that point we can see what needs to be done next. So I'm going to go ahead and pause the video at this point. Okay, so now we have designed the very basic SD card. What we've done is we've taken the SPI chip select, and we're putting it through a voltage divider along with the same for MOSI and CK, which is the SPI clock. And then we are feeding that into the SD card shield. Now, for MISO, we actually don't need to do that, a master in, serial out. With that particular pin, we can feed that directly into the AVR because it's going to be a high enough voltage for the AVR to be able to detect it. Now, having said that, we still needed to come up with a basically voltage regulation for 3.3 volt, but we are supplying 3.3 volt and ground to the SD card, as well as ground to the shield. I like doing ground to the shield. Some people like leaving it floating. I don't really see the need. Just for me, it makes it a lot easier just to ground it. And we've added some decoupling here. We have 7 ICs currently, so 7 capacitors here, and we can actually put a little note here. Let me see, C3 through C9. C9 equals 100 NF, 100 nanofarad standard. Yeah, we can just drop that right there. Okay, so that is the circuit for the SD card. And the next thing that we need to do is we need to add some voltage regulation here. So let's go ahead and go to this. Let's look for 1117. We'll use 1117 because it's a surface mount part, but it's actually a large enough footprint that you can solder it with just a regular soldering iron. The pads are large, so let's go with regulator. There we go. So it's a SOT 223 design. As you can see, it's a little bit larger like that. Got plenty big enough pads. So let's go ahead and use that, and we're not going to have room there. We'll put this over here. Okay, so we need to add a line for voltage, and we need to add a line for 3.3 volt, and we'll just name that 3.3 volt. Yes, we do want to connect it. Now we need some capacitors. This doesn't really require very large capacitors, so we're just going to go with probably 10 microfarad. 10 microfarad is a pretty decent capacitor for this. I haven't really had any problems with it. We do want to polarize though. Make sure you're always selecting the right package. Scroll down to find something that's going to be useful. I think that'll do, 1.8 by 4, and we will just connect that right there. Actually, what we will do is drop that down just a bit. Okay, and we want to make sure we connect them. And then with this, what we can do is connect all these to ground, and we will just put a label right here, and now we have our voltage regulation. And it's a very, very simple circuit. Essentially we're just feeding it with 5 volts and then couple capacitors here just to help it out, and then it's just going to spit out 3.3 volt on the other side. The 1117 is a very, very easy to use voltage regulator. It's just as easy to use as the LM7805, but it is actually a low dropout, if I'm not mistaken. I think it can take something, I'm not sure about the 3.3 volt version. The 5 volt version can take something as low as, I think it's like 6 volts. I'm sure that this would probably take something as low as 4, but I'm not going to pull up the data sheet just to find out. I know it works fine for 5 volt, at least the versions I have, so that's what we're going to plan on using. Now we do need to start thinking about how are we going to actually connect this to the outside world. Now we do have RX and TX, but we don't have any way of actually connecting those up to anything. So we need to actually add in some type of header here. So very simple way of doing this would be a 4-pin header. So let's look for that. Doesn't matter if it's male or female. I'll probably use male here, but I'm trying to think. What we could do is I've got the Spark Fun. Okay, Spark Fun connectors. Let's look for the FTDI. There we go. So this will, I guess, serve our needs, I think. That way we have a SparkFun connector on here. Now I don't think that we are going to need much, and of course I'll have to do some research to figure out exactly how you wire this up. Because I'm not sure if the TX and RX are already swapped. I think this is going to be RX in and TX out, so I'm pretty sure that we can just simply yeah, I think we can wire it up one for one. So let's plan on doing that. If it's wrong, well, we'll just have to fix that on a new rev, but for what we're going to do, it shouldn't matter really. We're not worried about whether or not it's compatible at this point. We just want to get the pins out there. We won't need CTS or DTR. They're useless to us because we don't have either one of those on board. Of course, we could rig this up so that the FTDI could reset it to be able to flash it, but we're more worried about you know, just getting some serial input. And since most people, if you're not going to actually use some type of USB you know, circuit, whether it be a CH340, you're probably going to use something along these lines. So this will at least just give you something to wire up to. So let's we actually need to rename this. Yes. That's VCC and G&D. Now the last thing that we want is a Arduino ISP. Let me see here. We can drop that right there. It doesn't have to be anything special. We just and we will rename these real quick. And we will drop some name pads. We need to clean that up just a little bit, but I think that it will work. And then, okay, so that's it. I think that's it for the hardware. So let's see what else we need. I can't really think of anything offhand. We've got a way to program the AVR. We have serial communication. We have voltage regulation for the SD card circuit, which we also have. We've got our address low and high bits for the AVR, and we also have our AVR interrupt circuit here. We have both our RAM chips already decoded, and of course our pull-up resistors for the Z80. We have our clock circuit for the AVR as well as our reset circuit, and then we also have our clock divider for the Z80. The one thing that we do not have currently is a reset switch, so we will need to add that real quick. Let's move this over. We'll just go ahead and move that right there. We're going to get a switch, but I like a very particular package. It's see here, see if I can find it. So this package right here, Omron switches. I'm not sure exactly what that is, but they've got an awesome footprint here for the standard little tactile switches. We don't need to do anything special with this. We're essentially just going to feed one side to ground. Well, I guess it would help if I had the bus pulled down here, so we will go ahead and do that now. Okay, let's go ahead and delete that, and we will come back here with a ground, and then we're just going to tie into that side, and then for this side we are going to use, actually no, let's do this a little bit different way. Let's tie this side to ground, and then this side we will make this the AVR reset. So we're going to rename this AVR underscore RES for reset, and we will add in a tie to there. So now we have a reset circuit for the AVR, and I think that pretty much completes our build here, or at least our schematic. I don't see anything else that we really need, at least for the time being. And of course this is a little bit more complex than some of the other Z80 computers that interface with an AVR. But I think it gives us a little bit more flexibility. And yeah, we're adding a couple extra chips, but that's nothing really special. One of those is actually just a 32K RAM chip, because we're using two 32K chips rather than a 64 kilobyte chip. So that means that we're actually two chips larger. One of those is this latch for the upper address so that we can do DMA, which most of those other computers don't really have something like that. And so that means that we're really only one chip more, and that one can be described as being this one here, because we are using this particular chip here in order to generate both the clock and the interrupt for the AVR, versus the other computers out there that simply just, you know, pin to pin. And I think the MBC, it actually uses one of the oscillator pins here. I think it's OC1A as the clock oscillator at 4 megahertz for the Z80. We're not so worried about that because, you know, this is a little bit cleaner way of doing it, and it doesn't have any software that it has to worry about there. So I think it uses a single NAND 7400 chip in order to do the address decoding and also the interrupt and the wait states. So we're doing it a little bit differently here, but it's functionally about the same. And I think this actually gives us a good basis for being able to build a computer. So yeah, I kind of like this. It looks like it's probably going to work pretty nicely. Now, I think I have all of these parts on hand. Of course, I've got a ATmega 16. I've got a Z80 here. I've got the RAM chips. I've got a 74 HC138. I've also got a couple of the 74s, and I've got a 74 574. I may not have this ISP header here, but I should be able to just use a couple pins. I'll just have to remember which way is the orientation. Of course, I can mark that with a magic marker or something. I've got a couple regulators, but of course for prototyping I can use whatever for that. That's not really a big issue, and of course it would have this entire circuit here on the card itself with the exception of the resistors. Tactile switch isn't that big of a deal. That's easy, and we're not so much worried about this because we can just grab the RX and TX lines and power and VCC to power it. So I think this is going to work. Yeah, looks good. Okay, very happy. Alright, so I can't think of anything that we need here, and of course I've renamed this to AVR_2, and we'll save that real quick just to make sure that we don't override it. And this will be the schematic for the second part. And of course I said I wasn't going to host much of this information on the website. I think I am going to just do a short little post, and I'm going to stick the schematics for that onto this, or onto the website. That way you can download the schematic and play along at home, or modify this to your own liking. So we'll go ahead and do that, but I think the next thing that we have to do is to prototype and make sure everything works. So I think that's going to be what we do next. I don't see any real flaws, so yeah, I think we got it figured out. Okay, so I'm not going to burn up any more time than I have to, because I know everybody has other videos to watch and their own projects to work on. So that's going to be it for episode 2. Still have 1 pin of I/O left over, and who knows, we might be able to use that as another chip select for adding in maybe a serial EEPROM, or maybe something else. I don't know. I haven't really decided. Maybe we can add a small little TFT through SPI or something like that. That might be neat. And of course, what we could do is just add a new page here, and we can add a frame. Let's see, I think I used this one for the last. Either way it'll work. Actually, no, we didn't. Let's which one did we use? Let's just go take a look. That's going to be the easiest way of figuring this out. Which one did we use? We used frame 1, letter L. Okay, so that tells us what we need. There we go. Okay, so now we have a new page, and we can add a little bit more to this as we need to. So maybe we'll add a TFT. That'll be neat. And then we could have, we could add a TFT to this. That would make it really easy to select the TFT as well. Now we wouldn't have much there to do anything with as far as the input would be concerned, but we might have a little TFT on board. I've got a couple of these little serial TFTs. I think that would be really interesting. Of course, there's already libraries for the AVR, especially with the Arduino IDE, so that's something we'll look at. We'll play around with the idea. I'm not sure I'm going to do it, but we'll play around with it. Okay, so I think that's it.
So that's it for today. I hope that you enjoyed the video. If you have any questions, feel free to comment below. Obviously, check out the website, www.retrodepot.net. And always, if you like these videos, subscribe. I try to post content like this as often as possible. Now, in this video, we went over some of the different things that happened in the last episode and how those don't quite fit our needs, and what we need to do to change that in order to make this computer actually work the way that we intend for it to do. So stay tuned. Next week we're going to be posting this same type of series. It's going to be video 3, or episode 3 if you will, and of course hopefully by the end of that video we have something that actually functions the way that we intend for it to. So I hope that you like it. If you did, like I said, subscribe. It doesn't take but just a single click, and you'll get to see more videos like this, and of course reminders of when I post new videos. Obviously, check out the website, like I mentioned before, retrodepot.net. And then, as always, if you have any questions whatsoever, any comments, or anything that you would like to add to the discussion, please comment that below. I try to respond to each and every comment. At this point in my channel, I don't have hundreds of thousands of subscribers or anything like that, like some of the other channels do. So I'm able to address these things on a more personal basis than some other channels are. And I intend to do that as long as it's possible. Right now, I think the channel count's only around 350 subscribers, but I typically have anywhere between, let's say, 1,000 views a month or so. So we get quite a bit of traffic. We just don't have a very large subscriber base at the moment. So again, I want to thank you for watching until the end of the episode, and again, we'll see you next week.